Hello, everybody. Welcome to Alex Derives Stuff. So today, what I'm going to derive is some derivatives. In particular, the derivative of the sine function and the cosine function. And what I'm not going to do is do the sort of classic intro calculus derivative of this using the limit definition of the derivative. We could if we wanted to, but that's less fun than what I'm about to do here. So this stuff is going to involve a few things about vectors and then a few geometric facts about circles, and we're going to bring in some like physicsy things like position and velocity and their relationships. So hopefully these are facts that everybody knows. Well, I don't know, you might not know it. It depends on whether you're taking calculus or not, but the derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. And of course, that negative causes all kinds of trouble for all kinds of people when they're doing these derivatives. It's like, wait, where does the negative go? All right. So there's some background stuff, some things we need to know to perform this. So one of the things we need to know is some stuff about vectors in R2. So R2 is just the x, y plane. And in particular, we need to know how the dot product works. So here's here's an example of the dot product. So suppose I've got two vectors. Say I've got v equals, I don't know, like 2, 1, and w equals I don't know, 3, -2 or something like that, right? Okay, so here's two vectors. What's the dot product of these two things? And so the way we say this is v dot w. And this is a way of multiplying these two vectors together to get a number. So it's basically the way you do it is first thing times the first thing plus second thing times the second thing. Okay, so 2 times 3 plus 1 times -2, which if you work it out is like 6 minus 2, so that's 4. Now, well, what on earth does this mean when we're doing this? How do we interpret this number that we get when we perform the dot product of these two vectors? Well, it tells you something about the relationship between these two things. So if you've got like a couple of vectors over here, so let's say I've got like that's v. Oh, that line's way too thin. All right, so let's see here. Here we go. So let's say that's v and that's w. All right, and so note like here we have an acute angle between v and w. And if we have an acute angle between v and w, then we know that v dot w is positive. All right, so I'm not deriving this, but the thing that is really important is that if the dot product is 0, then the angle is a right angle. So if we have a situation like this, whoa, where are you going? So if we have a situation like this, or if I've got v points that way and w points that way, and we have a right angle there. So then here we could say that, oh, if v is perpendicular to w, so v is perpendicular to w means v dot w is equal to 0. And then I suppose if you get a negative number, that means you get an obtuse angle. So for completeness sake, I will write that. So if I have v and w and we've got an obtuse angle, so w points that way, say, and so here v dot w will be negative, so that's an obtuse angle. Okay, and as far as angles between vectors go, well, you can't really get bigger than 180 degrees and so on. No, now we can prove all of this stuff if we like, without ever once referring to the notion of cosine and sine. And so since we're going to prove stuff about those, we want to use things that don't involve cosines and sines other than like the straight up definition. So all right, so we have this problem here using the dot product, which is basically just, okay, given a vector, AB, we want to find another vector, W, so W is the name of this vector, so that W is perpendicular to V and it has the same magnitude as V. So, well, let's see here. I guess first of all, what's the magnitude of a vector? Magnitude of a vector, that's given by the Pythagorean theorem. So if V is equal to AB, then the magnitude or length of V would be just the square root of A squared plus B squared. And notice that this is, so yeah, we would interpret this as like, how long is the vector? All right. Okay. So now if W is perpendicular to V, then that means that the dot product of W and V is equal to 0. So we just have to figure out a vector that, well, if I dot it with V, I get 0, and also it has the same magnitude as V. Okay, so that's what this problem here is, and we'll see when we get to our derivatives of sine and cosine and stuff why this is important. All right, well, let's see here. So let's say W is, I don't know, CD. Okay, so the W dot V would be, so V was AB, right? So it's A times C plus B times D. Now there's an infinite number of W's that'll do the trick here. Now, if we want this to be 0, well, it'd be nice if we could just make them both like one of them's AB and one of them's negative AB. So this is a standard little trick here that's worth knowing if you're dealing with vectors in R2. So a trick, if W, so we take the components of V, swap them, and make one negative. Okay, so in other words, if W is equal to negative B comma A or B comma negative A, like, so either of these vectors would be perpendicular to V, right? Because you could check if you do, yeah, because both of these, so the first one would give us negative AB plus AB for the dot product, and the second one would give us AB minus AB for the dot product. And so these vectors, by the way, are just, one's negative one times the other, right? So like they point in opposite directions, right? So if we're looking at our particular example of V was say that way, then one of the W would either be that way, the same length, or that way, the same length. So negative W, right? So both of those would be that. And so depending on the situation, you may have to choose here. So basically, yeah, this is a good trick right here. If we want to get a vector that's perpendicular to a given vector in R2, and this only works in R2, this doesn't work in R3, and we want it to be the same length, because you could check, right? The square root of B squared plus A squared. The negatives go away when you do this. Then, yeah, just swap the components, make one of them negative. All right. Some other stuff we need to know that, as you saw, like my scrolling got to. We need to know stuff about parametric curves in R2. So what on earth is a parametric curve? So a parametric curve is basically, you can think of it as position as a function of time, and this is definitely how I think of it. This is where it's getting a little physicsy here, and so all pure math people may shudder at me using the notion of time and whatever. All right. So this is perfectly good. This is what the inspiration for a lot of this stuff was, right? So imagine we've got some curve, right? So there's some curve, and say we've got a coordinate system here. So say like, oh, there's X, there's Y, and so this is our origin, right? So you can imagine like picking a point on the curve and drawing a vector from the origin to that point in the curve. So that would be your R of t. And so the idea is that if you plug in t, what you get out is the x and y coordinates of this point on the curve. And if I plug in like some later time, right? So R of some other time, R of then I would get some other point on the curve, right? So this vector would be r of like t2 or something, like some other particular time. Okay. And if we interpret this as time, then our velocity would just be the derivatives of these things, right? And it would be defined in the same way. And so, yeah, and then, in the limit as these two things approach each other, you get a little tangent vector. So we get a velocity vector at a particular time that would point tangent to the curve. So this is v of t equals r prime of t. And if we take the magnitude of this velocity vector, we get the speed at a given point. Okay. So the way this is going to work is, well, first we're going to define cosine and sine using something like this with the, our curve is going to be the unit circle. And well, we'll know something about the speed, and so we can use that to figure out what the derivatives of sine and cosine must be. Okay, so here's some unit circle stuff. So remember the unit circle, set of all points in the xy plane, so that x squared plus y squared equals 1. So let me draw the unit circle. So I'll draw my coordinate system here. So there's x, there's y. I'll draw a circle. Hopefully this is a decent enough circle. Close enough. And so the idea here is that like, oh, okay, so the equation of this curve is just like x squared plus y squared equals 1. And the idea is that, okay, if I plug in like 1, we could say like, okay, 1, 0, that's a point on that because 1 squared plus 0 squared is in fact equal to 1. Or, like you could do 3/5, 4/5, that also works. Any x and y that you choose such that x squared plus y squared equals 1 gets you a point on the circle. And if you remember the unit circle definition of cosine and sine was if you draw a little arc around the unit circle, theta is the length of that arc. And then if I then go to this point here, like the x coordinate of that point is defined to be the cosine of theta, and the y coordinate is defined to be the y coordinate is the sine of that length of that arc. So here, we're actually not treating theta properly as an angle, we're treating it as physical distance along the unit circle starting at 1, 0. So it's important that we start at 1, 0 and traverse counterclockwise. And this works here. If I walk far enough to get in any quadrant, so if I sort of like keep going, so to say like there or something like that, then I could say like, well, the length of the arc all the way around from there to there is theta. And then, yeah, then the x coordinate there would be cosine of theta, and the y coordinate there would be the sine of that angle. So these are strange functions, right? Like they're x and y coordinates as a function of arc length around the unit circle. Interesting. So an equivalent definition here. So now we're on this second bullet point here. So, well, rather than talk about arc length along the unit circle, we could sort of talk about position as a function of time, right? So, because basically, if I travel, so if I say like arc length, well, if I travel a distance 1 in time 1, then I'm going at a constant speed of 1. So this is going to be this thing, it's constant speed of 1 right here. So the idea is that like, oh, okay, well, I redefine this. It's the same definition. I'm just like recasting it in more, like physicsy type language, right? So there's my circle. So the idea is if I walk at unit speed right there, and then this position vector right here would be a radius. So that would be r of t. And then by definition, the x coordinate here would be cosine of t, and the y coordinate here would be sine of t. And the important thing here is this definition works as long as the magnitude of v is equal to 1. And so we could even draw a little like tangent vector here. So a tangent vector would point sort of that way. That would be a velocity vector at a particular point. And it would always have a length of 1 by definition, right? Because, yeah, we're walking around the circle at a unit speed. Okay. So a very, very, very useful fact about circles is that a tangent is perpendicular to a radius. Why is that? Well, okay, so it's geometry. You could prove that with ruler and compass if you like. Okay, so here's what we know about our thing here. We know that by definition, if we're traveling around the unit circle at a constant speed of 1, our position as a function of time is cosine t comma sine t. Okay, and we know that the speed is constant, and we also know that the velocity vector is perpendicular to this r of t. So then suddenly we're able to have a very, very, very quick proof here. So things we know about, so we know that position is r of t equals cosine t comma sine t. And then things we know about velocity are, well, we know that 1, the magnitude of velocity is 1 for all t. Okay, now note, by the way, the magnitude of r is also 1, right? Because x squared plus y squared equals 1, right? Because every point on the unit circle is a distance of 1 from the origin. Okay, so note that the magnitude of r of t is also equal to 1. So these guys have the same magnitude. We also know that v of t is perpendicular to r of t at any given time. So we know that v of t dot r of t is equal to 0. Okay. So with these two facts right here, we get two possibilities for our velocity, right? So our derivative. So therefore, by that first trick that we did with the vectors, so the v of t, there's two options. You know, you take r of t, and you swap the x and y components and make one of them negative. So it's either negative sine t cosine t, or it's positive sine t negative cosine t. And I guess at this point we have to decide, like, well, which one is it? Okay. Well, let's scroll back up here to our little picture here. Well, the v is supposed to be pointing in the counterclockwise direction, right? So the v is pointing in the counterclockwise direction. Okay, so if we pick a t where we end in, like, say, the first quadrant right here, well, okay, so this v, well, clearly so here, clearly, like, these are both positives if we're in the first quadrant, the x and the y. And so this green v vector over here, it has a negative x component and a positive y component. So the negative should be in the x slot of the v vector. Oh, okay, so basically, so that means this is our guy right here, right? That's the one with the negative sign in the x spot, and that'll make it point counterclockwise. And we're basically done, right? Like, well, we now, since v of t is going to be the derivative of r of t, so then we know therefore, so the derivative of cosine t is negative sine t. Why? Because, well, oh yeah, well, the v of t was negative sine. Yeah, like, okay, so cosine was r of t, negative sine was the x component of v of t. All right. And then also, the derivative of sine t is cosine t. Bang. So basically, what happened here? This seems like a cheat, right? There was no limits. There was no crazy algebra here. It was all just sort of like trickery with, like, drawing tangents to a unit circle or whatever, and then just noting that the velocity was 1, or the speed was 1, I should say, right? The velocity is like this vector, right? The magnitude of this velocity vector is always 1. But that's something that was done by the construction of the cosine and sine functions in the first place. So this sort of has to be true. And then from this, we can infer lots of other things about the sine and cosine function. And in fact, if we just include starting values with cosine and sine, so since I'm at the point 1, 0, right, t equals 0, that gives us cosine of 0 is 1, and sine of 0 is 0. So if I just use these two properties where, okay, if I have the derivatives of cosine and sine as such, and I know that cosine of 0 is equal to 1, and sine of 0 is equal to 0. Believe it or not, just these two things right here are enough to figure out anything you need to know about sine and cosine. It takes a bit of trickery to do that in some cases, but like you could figure out, for instance, the Taylor series for sine and cosine just using these two things as starting points. All right, I hope you enjoyed this cool little derivation of the derivative of cosine and sine. It's quite a bit different than some of the derivations of derivatives that you may have seen before. So yeah, it's nice to do geometry stuff, I think. All right, so stay tuned for whatever it is I do next. I think I might do some more sine and cosine stuff, actually.